I'm so excited to be here. I am, as you can tell, not a Pythonista, but I have one in the family. And Glyph gave a talk a few weeks ago about the future of programming, in which he talked about his midlife crisis, among other things. I'm past the midlife crisis. I'm retired. Yeah, just for a quick show of hands, how many people here are retired or planning their retirement? Oh, wow, excellent. So 3 or 4 of you will be able to appreciate the talk. And for the rest of you, I'll try not to dwell on my retirement, because what's past is prologue. So Richard Hamming, one of the inventors of networking, and also a lecturer about science and engineering, talks about how you must adapt your style to fit the future, since merely copying the past will not be enough if you aspire to future greatness, a matter I assume and we'll talk about often in the book. And there's also a video of him sort of talking about this material on YouTube. And so I want to talk about the future of programming in that sense. That it's what's past is not necessarily what the future is going to look like. And so a bit of my bio, and this would be sort of like, say, a hypothetical example. Supposing you start out as an APL programmer after you get your degree in computer science, and for 7 years you're an APL programmer, work your way to the top, be a senior engineer, really good at what you do, and then you realize APL isn't the future, and so you become a C programmer, and you spend 7 years becoming an ever better C programmer, becoming a senior engineer, and then at the end of that you realize that you kind of wish for that productivity that you had from higher level languages, so you become a small talk programmer, and you work your way up as a small talk programmer. You spend 7 years becoming a great small talk programmer, and you realize small talk isn't the future, right? Until you become a Java programmer, and you spend 7 years becoming a crackerjack Java programmer, right? So now you're 28 years in, and the web is the thing. So you're going to become a JavaScript programmer, spend 7 years, become a crackerjack JavaScript programmer. But you see where this is going. It's like the reason that Hamming, when he's talking about how people need to think about the future is not the same as the past, and excoriating all those senior managers, taking up, using up oxygen in the office and doing things the old way, is because every 7 years or so you sort of face this crisis where you have to say, can I keep making money like I'm a senior guy because I got experience doing that old thing, and I keep doing that old thing because it's still pretty valid, right? I could still be a Java programmer. Or you want to see if you could find a job as a mid-level engineer. You don't really have 2 years of JavaScript, but you're pretty smart. You've been around for a while. Maybe you get some life credit, right? And sort of work your way up. That was only 4 cycles, right? So when you're 6 cycles in, and you've been at it for 42 years, and now you're thinking about the 7th cycle, that's when retirement looks like a really good option. So anyway, I tried to live my life by the principle of this book, which I read when I was in high school, which basically says, don't, keep reinventing yourself. But that in fact you can't, because you'll keep getting promoted until you get to the point where you're not good anymore. You can't promote you anymore. So you're going to be stuck doing that for the rest of your life. So I'm retired. And what I should probably do now, because I can do the things that I might do for the future of programming, don't have to be commercially viable. They don't have to be good for my career. They could be what I think the right thing to do is. That's awesome. Now, if I make the wrong decision, it's on me. Python is where it's at now. Everybody can see from this graph from Stack Overflow. But the thing is, I keep getting accused of being an original thinker. So I'm going to try to to do the right thing that everybody else is doing, but I might fail. So what I'm going to do is talk about, I don't want to be didactic and tell you what you should do because most of you are not retiring. But what I want to talk about is what I have been doing in the year and a half since I started retiring, what I'm doing right now, and what I'm going to be doing once I finish with that. And everybody knows the future is mobile. Apparently doesn't work through the body. Everybody knows the future is mobile. It's sort of common knowledge. So everything that I'm going to say here today, presumably, hopefully, is not original. It's stuff that you all know, that you've heard lots of times before. I like putting up this graph, sort of showing how the mobile ecosystem is sort of taking over from desktop computing. That if we think about computing in the future, computing isn't about computers, it's about mobile stuff, which we can say, you know, we can call them computers, but they're not really. And the reason I like this particular graph is because it doesn't do this. And for Maggie, who's attempting to write this down, transcription, this is sort of the whooshing move with the right hand up and to the right to signify exponential growth, which is what you want in all of the business charts. You know, and this doesn't do that, but it sort of gets across the point that mobile is where it's at. Mobile is growing. We should all be mobile, and so everybody does mobile. So what do you have? You have this architecture because you're web-based, because web was the thing, right? The last 7 years, and now we want to be mobile. So this example, you know, for I used to work in e-commerce for a while, right? You have a product catalog, then you have a web application server. People browse your catalog by going through the web application server, and then you have sort of the in-house people who sort of update the catalog, and they use a different application, so it's a different application server, but mostly they import and export stuff with spreadsheets, so you have that. And this is the architecture that most people use for this kind of a thing. And now we're going to be mobile. And that's the new mobile architecture. You catch it, huh? So if you look right up there, it's because there's an app, right? Probably written using some kind of WebKit wrapper, you know, so you can keep all your JavaScript and HTML, and now you're mobile. But the other cool thing is serverless. So now we want to be serverless. And so what you can do is yeah, now we're serverless. So we take all of our Python code or PHP code or whatever it is, and we put it, you know, Node, and we put it in lambdas. And I couldn't decide whether it's a herd of llamas and it's a fall of lambs, and I couldn't decide which was the correct collective noun for a lambda. But you know, please, if anybody has any ideas or would like a coinage, let's do that. So we can use Cordoba, and we could use lambdas or Azure functions, and then we'll sort of be mobile. But the thing is, I came of age in an ancient time, and I remember when this article came out by David Eisenberg, The Rise of the Stupid Network, and this is sort of a recurring theme, right? So the rise of the stupid network. This is about telecommunications, but I think the underlying principle still holds true today. The point being, and this was all about TCP/IP in the ancient times. There was sort of this debate as to whether TCP/IP was a good idea or a bad idea. All the telcos said it's a bad idea. And you know how you know it's a bad idea? Because what it does is it makes all of the network traffic the same. There's no intelligence in the network. And if you are a company that sells networks, your differentiation is how intelligent your network is. So obviously, intelligence in the network is really, really important. And they had this thing called ATM. ATM stood for asynchronous transfer mode. Right? So ATM networks were better than regular networks. And one of the things that I love about the web is we keep repurposing three-letter acronyms and three-letter names so that they used to mean one thing and now they mean something else, and then old people get confused like myself. And when you say ATM, I have to say, are you talking about bank stuff? Are you talking about phone stuff? The web, actually, the original use of the word web, Donald Knuth's book about literate programming, for those of you who want to check it out, he developed this system for doing literate programming, which he called web. And then he explains in the text that the reason he called it web is because web was the only three-letter word in the English language that wasn't being used for something in computers. So anyway, the idea of the stupid network is you don't put the intelligence inside the network, for asynchronous transfer mode and do different kinds of content, use different kinds of network intelligence, but you put the intelligence at the edge of the network where the intelligence belongs. And so if we think about, so what would that product catalog app look like if you were trying to be mobile? It would look like that. You take the database and you put, because we have mobile things now, and these mobile things are not stupid desktops, right? They're smart desktops. They have gigabytes of storage, right? So you could put your product catalog in the client, right? And the only issue that you have, if you think about it as a data flow problem, is when somebody wants to update the product catalog, how do they get their updates over to the people who want to know about the updates? Right? And so the network is just like the phone network, right? You're just trying to transfer the information. I did an update here. Everybody who's interested should get the updates, and there's no intelligence in the network. And in fact, if you still want to do the spreadsheet copy-paste stuff, you're actually copying and pasting from one place in your machine to another place in your machine. So it's like it's actually built into the operating system. You don't really have to do that much in order to implement that kind of stuff. And the difficulty, and I apologize, and this is why I called it a tragedy in 5 acts, is because the places where you would write the Python code aren't on this diagram. So, I'm sorry. I wasn't thinking languages, I was thinking architectures. And this pattern, make 2 observations. So people see the iCloud thing and say, oh, iCloud is like a storage layer. But if you read the documentation for iCloud, they're very specific about that. They say it's not a storage layer. Don't use it as a storage layer. You don't make requests to iCloud to get data because that won't work. And I said, what do they know? I got 42 years of experience. So, so I wrote an app that used iCloud as a storage layer, and it didn't work. Because they were right, they designed it to be a store and forward layer, right? So the idea is you could do backups there, and you can retrieve your backups, and you can send messages to be stored and forwarded, but you can't use it as a database, not a database kind of a thing. But nevertheless, for that application that we were just looking at, it sort of kind of works. Actually, it works pretty well. And this is a pattern that replicates itself onto all kinds of things that people do. So the other one that came up is, you go to a restaurant or you go to some shop and there's a greeter, right, who's got a mobile device, right, and they want to put you on the waiting list, right, to let you know when you're at the head of the line, so you don't have to stand there and wait in line, right? And so what does it look like? Well, they have their mobile app, and there's a web application server that takes their input and puts it in the database, and then you can check the database to see where you are in the queue. But then, of course, we're mobile, so we get a Twilio account, and we text the customer from the middleware because it just sort of pulls the database, gets events. We can use r0ml or something like that. Here's the thing, though. Mobile devices have texting built in, so you could do it this way. Actually, it's not even clear that you need the cloud at all. Right? And the only shift that you have to make is, where does the database go? The database goes in the machine of the person who's, updating the data. So I'm going to wax political now. I'm going to channel Richard Stallman for a moment, right? Not only do applications not need servers, right? Having a server is unethical, right? So if right, if you think of what's destroying Western civilization, right? And I don't want to offend any of the sponsors to whom I am very grateful that they invited me here through Chris, to tell you all of this. But, you look at Twitter and you look at Facebook and what is it, that drives all of this stuff? It's that they collect all of this information in these vast databases, which they would never use for malfeasant purposes. They would never mine these databases and send spam to people. They would never mine these databases to spy on people, right? No, that would never happen. Unless, they weren't making their quarterly numbers. And then they might. reluctantly. So anyway, so if now, and there may be some applications where you do need a server, right? So my example that says, oh, you just put the product catalog on people's devices, it's like, well, that wouldn't work for Amazon. That's what I always get when I do this talk at an architecture conference. Oh, that wouldn't work for Amazon. So yes, and it wouldn't work for jet.com either. All right, so how many other people have catalogs that are bigger than a gigabyte? It's like if you figure 1,000, bytes per thing in your catalog minus the picture, right? And you had a gigabyte to spare, you get 1 million SKUs in your catalog, right? And so, rounded to the nearest percent, right? 100% of the people it would work for, right? Right, and it wouldn't work for Amazon and jet.com, and I concede, right? So we'd have to think about something else. But in general, if you could build stuff, right, that would save civilization because you could show people how to build applications that didn't use servers so that you wouldn't be building spam bots and server farms to spy on people, right, then yeah, that would be an awesome future. So let's do that. So that's what I was going to do. And the thing about mobile, when so I say mobile, everybody's thinking here smartphones and iPads, right? Because that's what everybody says when they mean mobile. But I don't mean that. And this is a hard book to read, by the way. But it's gripping in the sense that when you start reading it, you get about halfway through, you're just like literally sitting in your chair, yelling at the pages of the book, right, to the characters, going, "No, don't do that! Don't do that! It's evil!" Right? And so be forewarned, it's a difficult read in that sense, but there's a whole section in this thing where he explores in great detail this concept of, he calls them localizers, but smart dust. Right, that is computers that are so small that they're size of dust, so small that you could sprinkle places, there'd be 1 million, you would inhale them, right? So part of the plot hinges on things like, if you've inhaled a bunch of computers with sensors in them, right, it knows when you're about to lie because it can see that your heart rate is going up, right? You can sense, it's like, the dust motes on your skin can sense that your perspiration is increasing. So you have all of these like weird things that he kind of thinks through, and it wasn't actually just science fiction. In 1992, Rand Corporation sponsored, DARPA, who writes, like, what if we could build smart dust, right? Are there any weapons implications? And so people sort of started thinking about this thing. When you think mobile, you're thinking smart dust. And if you think about mobile computing as smart dust, where would the server go? Well, you wouldn't have servers. The whole point of the smart dust thing was all the pieces of dust talk to each other, and there really wasn't a server. And the other thing about mobile computing is that the most common mobile computing device nowadays is an automobile. Right? A modern smart car has about 100 million lines of code in it. Right? It's got more code in it than OS 10 or Debian. And curiously enough, Tesla goes and hires the guy from Apple who developed Swift because if you ask the question, we'd be talking about, so what would you program, mobile devices in? What would you program a car in? So I want to learn that stuff, whatever that is. Maybe it's going to be Swift-like. Right now, I think they use C++, right? And it could be Python. But there's, if the global interpreter lock were sort of holding the process that needed to be deciding whether or not breaking was going to happen now. Right? And somebody had a patch for that, and they sent it to Marietta, and they said, 1,000 people are going to die if you don't take this patch. Right? Like, I feel sorry for, right? It's like, so it's unclear that Python is ready for this challenge, and it might be, and maybe we can make it ready for this challenge. But in any event, I'm not thinking about like the programming languages that one uses to do this. But there is a project to try to make this happen. So it could happen. And so the last thing that I want to do in the second act is to bring up a slide because some Moshe in particular was giving me, saying, "Oh, the last talk you gave at a Python conference was so great. I hope this one is as good." No pressure, thanks, Moshe. This is a slide from that talk. So Jerry Sussman, who's one of the authors of this book, and this quote was my freshman advisor when I was studying computer science, probably convinced me to go into computer science from this thing, right? This notion that software was a literary thing, and my whole talk around PyCon 2007 was built on this idea that programming was a literary art, and it's about understanding the algorithms and that being, human readable and maintainable and all of that was sort of the primary purpose of writing software. And whether or not it ran on a computer was kind of a secondary, happenstance. And I believed that, and I talked about it for years, and I sort of and now I'm thinking about those breaks. And if it's like really readable code that doesn't actually work right when I need to break, I think I've changed my mind. So the thing being that, in fact, when you start thinking about programming as a mobile activity and not a computer activity, when it's a bunch of computers that people have on their desktops, you're calling up Vannevar Bush's Memex essay from 1946, in which he's talking about that sort of how human knowledge exchanges and the motivating ethos of the web, that it's really all about exchanging information between humans. But when you're talking about making devices, right, thermostats and automobiles and cars and smart dust behave appropriately for whatever your definition of appropriate is, maybe the fact that they actually work properly in the real world is more important than whether or not the source code of the dust that you're inhaling could be legible if you could find some place to print it out and look at it, which it's unclear that you would necessarily have such a place. So much for mobile. So learning mobile was kind of what I was doing. Once I decided, I was going to retire, I started working half-time, and then eventually, quarter time, and then no time, and decided, I want to learn how mobile stuff worked. And what I've just started doing is learning how GPUs work. Like, why GPUs? Well, so I found this graph on an Apple-type site showing that, from mid-2006 to late 2013, the fastest GPU option went from being 5 times faster than the CPU to 30 times faster than the CPU. And that was sort of the latest one that I could find. Then I found this article about, you could program GPUs in Julia, and they had some benchmarks over there. And this was from 2018, in which they said, you pretty easily get a 60x speed up if you write things on the GPU instead of doing them in the CPU. Maybe you get it up to 80, and Julia isn't even the native thing that people program GPUs in typically. Right? So okay, so it's much faster than CPUs, and why would you care? Well, you would care because it started for doing graphics processing, which is why it's called a graphics processing unit, right? But then it started analyzing images, as long as it had all these images that it knew how to do stuff with super fast. And then people started figuring out other things that you could do with it, like blockchain mining or deep learning or machine learning. And so you could program those things, and they have their own programming language, right? Now apparently you can program them in Julia. And maybe you could program them in Python, right? But this is where I start thinking about sort of waves of technology and how they happen. A couple of things. So it turns out there's a website where you can get Python for IBM mainframes. Just quick show of hands, how many people are doing Python work on IBM mainframes? I thought maybe one of the retiring guys maybe could be doing it, but but not even that, right? Nobody programs Python on a mainframe, right? It's not the language that you use to program mainframes. You use COBOL to program mainframes, right? And why do you use COBOL? Well, because it was the #1 programming languages for business applications. It was designed to be easily readable and easily modifiable, and was designed to be portable, right? Just like for the Wintel architecture or the Lintel architecture, Python, right? It's the #1 programming language. It was designed to be readable and portable. So I was thinking about putting this in a slide, but I figured I would just say it, right? Python is the new COBOL. right? It aspired to be, right? So in the Wintel environment, which if computers continue to be the place, because I could be wrong about all this, if computers continue to be a place where people are writing code in the future, right? It wasn't that Python displaced COBOL, right? COBOL was the leading programming language for that platform, and it still is to this very day, and I actually know people who are still COBOL programmers on mainframes, right? They make a good living. And even if you had something better like Python, nobody's going to go back and like rewrite all that old stuff. Like, it works fine in COBOL, good enough, right? You move on. So if, and this is just all hypothetical in the future, if people are moving all their programming into GPUs, because GPUs are 60 times faster, right? Who's going to give up like a 2 orders of magnitude performance improvement, right? Nobody's going to take whatever that programming language is and rewrite all the Python code, right? All that Python code's still going to be here 40 years from now, right? Python will still be good at what Python is good at, but what will people be programming GPUs in? How do you program a GPU? How many people have programmed GPUs here? Couple? Okay. So for the rest of you who haven't, if you're sort of interested in programming, sort of seeing what it looks like, there's a couple of websites. These are sort of interesting websites. You can go to these websites. They show you the GPU program. They run the GPU program. Because it turns out on the web, you can download a GPU program. It puts it in your GPU and sort of runs it right there. So it works over the web. And you can sort of see the source code of everything that you're doing over here. And the way it works is, so it used to be when one did graphics programming, one sort of wrote code using libraries and it ran on the CPU and then it did graphic stuff. And the whole point of the GPUs was you don't do that. You download code into the GPU and you run the code there. And then what you do on the CPU is you talk to the program on the GPU, right? and I believe this reflects what we will call Rommels' third law. And I don't have time to go into Rommels' first and second law, but I will be in the hallway, and around for lunch and everything like that. So if people want to discuss further, we can talk about that. The third law says that any distributed system based on exchanging data will eventually be replaced by a system based on exchanging programs, which will work better and last longer. That's the hypothesis. Here's my proof points of things that worked that way, right? So SQL, and that's what made the whole distributed thing possible. Right? You had mainframes, and everything ran on the mainframe. And in order to have it not run on the mainframe, you would have like some program running on something which was not a mainframe, mini computer, workstation, personal computer, etc. And then it would have to talk to the database. And initially, the way you talked to the database was you transferred data back and forth, right? You made API calls to the database. And it turns out that if you're being distributed, that's too chatty. So what you want to be able to do is send a program, which SQL, it's a Turing complete programming language. You can say, hey, run this program for me and give me the result. And that has survived in the effort of all kinds of things to kill it. And people keep saying, oh, the reason SQL survives because we have all these great new NoSQL databases is because they're these old programmers, who've been doing it for 42 years, and they know SQL, and they're going to keep using SQL because you can't teach an old dog new tricks. And that could be true. But if Rommels' third law is true, then what that means is the reason people keep using SQL is because nobody has bothered to write a better Turing complete programming language that you could talk to a database with, right? So all of the NoSQL databases eventually wind up putting a SQL layer on top so you can talk to the database using a Turing complete programming language. But what they could, and complaining about the old legacy guys or gals, but fewer gals that are that legacied. Or they could, invent a programming language that would do these things pretty well. So what else? Postgres, right? Desktop publishing. The desktop publishing revolution. How did that work? Well, there was this variant of Forth that you could send to a printer. You could say, oh, printer, I want you to do complicated stuff. Let me send you a program. Right? And you would write the program, or you would generate the program, and you would send it to the printer. And that, I claim, is what made desktop publishing actually work. And then it worked for years and years and years and years. Right? And then the web. Right? The web was HTML and CSS, and that didn't go very far. And when did it turn into a real thing? It turned into a real thing when there was JavaScript, when there was a Turing complete programming language that the server could send the client and say, here, I want you to do some fancy stuff. I'm sending you a program. Right? And GPUs, you want it to do fancy graphic stuff, you have to send it a program. And when I saw that, I said, aha, that means this is a thing. Okay? Now, the counterpoint to Rommels' third law, of course, is then once that happens, everybody says, oh, that's a security problem. Let's fix that by inventing a way to solve this problem just by exchanging data, right? So it's like, oh, we'll do CSS HTML5 and CSS3, and then we won't need to use JavaScript for all of these things that we need to use JavaScript for, right? Or we'll invent NoSQL databases and GraphQL, right? Oh, then we're just passing data back and forth, and it's really not programming, right? PDF, so we don't have to do PostScript. It'll just be like a data format that we can send back and forth, and it won't be actual programming. So possibly it like oscillates, like it's a phase, it's a light, it's a particle, or it's a wave kind of a thing. Maybe it sort of just oscillates between these two modes of being back and forth. But I view it as it only catches on when you have a programming language that you can talk to it with, because that means it's so complicated that you need programs to do it. And then after you've been doing it for 30, 40 years, you say, I'm beginning to see some patterns. Maybe I could solve a lot of these problems with some data format that would sort of cover the space, right? And you try that. Right, so that's my hypothesis. So since you have to put a program into a GPU, I got super excited because it reminded me of where I started out, which is as an APL programmer, right? So this is sort of my go-to. This is an old slide. You can tell because I use a different background scheme for old slides. So a talk that I gave at the Recurse Center a while back, and this is the program that solves Sudoku puzzles of arbitrary size. Now, I included the YouTube video. It's a 9-minute and 42-second video. I encourage everybody to watch this video, particularly in light of Moshe's talk about like exploratory programming. Like he does the exploratory, he derives this entire program online, showing each bit as he's putting it together in 9 minutes and 42 seconds. Now, I'm an APL programmer. I did it for 7 years. It was pretty good. And I had to like stop it every 5 seconds. And it took me about 4 hours to watch the 9-minute and 42-second video. So because I want to understand, and you don't have to sort of go into in that depth, but just as a kind of what exploratory programming looks like if you're using a high-level language, I would urge people to sort of see that. But the reason I taught, and that's a little too. All right. So this is a simpler APL program. This is the program that does one generation of the game of life, right? This is the definition of the function life. You give it a position, and it gives you the next generation. Right, and so the thing about these APL programs, which is what I'm sort of excited about GPUs is because APL took this approach that said, computers like to do things over and over again. They like to do things on arrays. They don't like to do things on scalars. So in fact, it's not possible to write a program that only does things on a scalar. Right? You can't have an integer in APL. You can only have an array of integers. Right? And if your array happens to only have one integer in it, well, okay, right? That could happen. Right, but there's no loops, there's no maps, there's no nothing, right? It's just like if you do this program, like it'll somehow deep in the bowels, it'll do it for all cells in your matrix magically. And if you understand how APL works, then you sort of understand the magic. And GPUs have that same flavor, right? When you program a GPU, you write a program, and you're told ahead of time this program is going to run. There are going to be at least 2,000 threads running concurrently, and each pixel on the screen is going to get its own thread. And there's no way in the program to say, yeah, but I'd like to loop over the pixels. Right? It's like, no, that's not a thing. Right? Some other agency is going to call you, over all of these pixels. Right? So, in fact, the thing that when I saw that I said, oh yeah, I have to learn how to do GPUs, is there's no random number generator function, whatever, in the standard library for GPU programming. Right? Because random numbers, the issue with a random number function is not like, oh, give me a random number, because that's not random, right? Because then if you say, oh, give me another random number and it gives you the same random number, then it's not a random number, right? So it's not that it gave you a random number, it's that the next number is going to be a different one. Right? And in a world where there's no such thing as next, because it's going to do them all in parallel, what does it even mean? Right? In this pixel, I want a random number, and I'm not coordinating with anybody else. So what do I do to say, give me a random number? because I don't know what the other pixels are doing, right? And it might wind up being the same one. So nobody's figured out. And I thought, oh, okay, so these things that you kind of take for granted are completely different. There's something about like how your brain has to work in order to understand this that I would love to spend some time learning how to do. And last, well, not last, Act 4. Deep learning, machine learning, AI. So we're going to talk about this not in as much depth as Lorena did yesterday, so I apologize if we're going to cover a little bit of the same ground. But hopefully I will fail to explain it as concisely as she did, and we'll go somewhere else. So why are we talking about deep learning? Well, because here we are in 2018, where the red says GPU. Apparently, more deep learning is being done on GPUs than anywhere else. Certainly more than being done on CPUs. And the trend continues, and eventually, apparently, according to this projection, it's going to turn into ASICs. So a little early for that. That's 7 years out. So maybe in 7 years, I'll be thinking about learning how to do something ASICally. But for now, so machine learning seems to be a GPU thing, and we've talked about GPUs, and so let's talk about machine learning, deep learning, artificial intelligence. So it turns out that Gerald Sussman, who thought that the whole point of programming was in order to explain algorithms to people, was an AI researcher, and this was his dissertation, his PhD dissertation. It was called A Computational Model of Skill Acquisition. Here's a sort of a random page from that thing. But basically, the whole point of the approach that people took for that kind of thing was, in his model, was there were 3 sections to the model. So the first section was the section that did the stuff. Right? And this was an architecture thing. So it would build arches and buildings and whatnot. You give it a bunch of blocks, and then it would build stuff for you. You'd say, build me this, and it would build it. And then there was a second piece, which was the evaluator piece, which would look at how the first piece did what it was supposed to be doing and concluded whether it did it well or poorly. And then sort of came up with some hypotheses as to what went wrong and what could have been done better. And then the third piece was the piece that was a programmer. So he refers to it down here. The and trick takes on the responsibility of code writing. Right? It changed the first program. So its job was, how do I rewrite this code so that it'll work better? Because the whole idea, which sort of informs where we originally came in, that the whole point of programming was to explain algorithms to people. He also believed that the whole point of programming was to explain algorithms to computers, and one of the things that you did with algorithms was, you wrote algorithms to make algorithms better. So the algorithms were just data. And so programming languages of the day had ways of taking strings and turning them into functions, and functions turning them into strings. So in APL, if you had a string, you could quad fx it, right, which means fix it as a function, and it would turn it into a function. And quad cr of a function would say, give me that function as a strings so that I can modify it, because I don't like the way it works. In Smalltalk you could compile stuff, but you couldn't. They really didn't have a mechanism for saying let me muck with it, except doing it at the byte code level. Lisp also let you define functions, and Java has a way which is too complicated to show in a one-liner. But you could also define things on the fly. But how do you define a function in Python? You look it up on Stack Overflow, and they say, use eval. See, but eval is a different thing, right? If you have a string and you eval it, maybe it defines a function, and maybe it does something else, right? Whereas all of these other things are, if you do that thing, it either defines a function or it fails, and then you don't get a function. But it doesn't run arbitrary code, right? In Emacs Lisp, you can do something like this, and so you can define a function, and then if you look at the function, it'll give you back the definition of the function as a data structure, and then you can operate on the data structure. So in this case, we're showing oh, give me back the definition for the function square, and get rid of the header, and let me just look at the steps in the algorithm. Right? So you could do that kind of stuff, and we don't do that anymore, right? And machine learning or deep learning or all of that, so the evolution from AI being a thing where you worried about programming and changing programs and having computers reason about programs, to, it doesn't do programming anymore. The computer science take on this is that there are two architectures. And in the beginning, they were all von Neumann architecture. And a von Neumann architecture means there's one bus and data and or code moves across it because there's no difference between data and code. It's just bytes. Right? And that's a von Neumann architecture. And a Harvard architecture says, no. Data and code, they're completely different, right? They're like waves and particles, right? They're totally not the same thing, right? And so therefore you have two buses, one for moving code and one for moving data. And this is more efficient in the case where you're moving both code and data because you can parallelize those two. But what it does say is, yeah, stuff that you could do with data that you can't do with code, and stuff you can do with code you can't do with data because they're different. And so the question is, are code and data the same or different? And recently, Google did Alphago Zero. Right, so they wrote a program to play Go. When I was in school, in computer science, right, there were chess-playing programs that were sort of okay. They still weren't at the level of competing internationally. But we had a couple of projects trying to figure out, was it possible to build a computer program that could tell if a Go game was over or not, and if so, who won? Right? And at the time, it was unclear that that was a solvable problem. And so then Google goes and builds AlphaGo, which defeats the world champion Go player recently. And so everybody's like super impressed. And then they build AlphaGo Zero, right? And the key thing about AlphaGo Zero is it's better than AlphaGo, right? So it's even better than the best program that ever was. It's better than the best human that ever was. But what was different about AlphaGo Zero was they didn't put any algorithms about how to play Go in the program. They just wrote a program that knew the rules of Go in terms of like, what are legal moves and what are not legal moves, and then had it play against itself and improve the algorithm randomly until it got so good that it was better than anybody in the universe. Now, I don't know how that works exactly. Right? So I read the article, but so I said, I want to know how that works. But there's a couple of things about what they did with AlphaGo Zero, in addition to what I just mentioned, which I want to call out. And one was that the original AlphaGo used two neural networks, what they called a policy network, which selected what the next move was. It was sort of the thing that analyzed the board position, say, do that move. And a value network, which is a different neural network, to predict who it thought was ahead, which was different than figuring out what you should do next. They had these two neural, and one of the things AlphaGo Zero did was it got rid of the two neural networks and it made one neural network that did both things. And I thought, aha. So is that kind of operation where you can take two neural networks and combine them, right? Is that composability generic, or was it just for this one thing? Because if it was generic, then there's some implications. But before we get to those implications, when they talk in AlphaGo Zero about how it became better, it didn't become better by changing any code, right? It became better, because this is what we learned from Lorraine about the difference between AI and deep learning, is, right, there's this machine model, which is data. It's not code. Right? So it made the data better, and somehow by making the data better, then the behavior got better, but without changing any of the code. So if I think about this from an open source perspective, if you just have the one program and the program never changes, but the behavior varies depending upon what data you feed it, then is not the behavior of the program really determined by the data? And if you believe in the GPL, then wouldn't that mean that you would have to publish all of your data in order to reproduce this program? Right? So, well, no, because code and data are completely different, right? It's like waves and particles, right? And GPL believes that, which is why there's a GPL and a GFDL, because documentation is encoded state, and so you need a different license. But I started thinking about that, and so if we get back to this composability thing, right? So if you have a neural network that can do handwriting recognition, say, and you have another neural network that can do voice recognition, say, and then you could build a neural network that could look at two inputs and decide whether it was digitization of some handwriting or digitization of some audio, could you then build by composing them a single neural network that could either do handwriting recognition or voice recognition, depending on what you hooked it up to. And if it could do that, could it also do image recognition? And if it could do that, could it also drive a car? And if it could do that, could it also write Python code? Right? So could there be one program that just does everything if you gave it the right data? I don't know. But I would love to find out. So that's why, and if Lorraine is still here, maybe you could also write telenovelas. So that's, right? And it could do interface builder, right? Interface builder is another case of this Harvard architecture, von Neumann architecture, right? So I used to be a big believer in, write all your UI stuff as code, right? Because then you could replicate it and you could do all kinds of, array-based things and you could modify it. But Apple keeps pushing you to use these zip files, which are just these data files. And in fact, if you write an app on the App Store, you're not allowed to dynamically load code, but you are allowed to dynamically load a zip file because it's just data. So if you wanted to change the user interface on the fly, you could have some AI that sort of optimized your user interface and could do that in real time and reload that stuff. And I'm getting the hook. It says 0 seconds. So I'm going to wrap it up, right? So the cognitive dissonance that we have here is, and I won't be able to talk about this in as much detail, is that widely distributed applications are moving to the Harvard architecture mostly for security reasons, right? So if you let people modify the code, then they could inject bad code, and so you don't want to do that, so you want to treat code different than data. They can modify the data, but they're not allowed to modify the code. So Harvard architecture is winning in the mobile area. Right? On the other hand, we've just agreed with Rommels' third law that new architectures only succeed if they use a von Neumann architecture, meaning you can download programs into it that tell it to do complicated stuff that you don't know how else to do it. And so the only way that we can make progress is if we figure out how to resolve this tension. Either we can figure out how to make von Neumann architecture secure, or we figure out how to make a distributed system work in a Harvard architecture. And is this deep learning thing where you say, I don't need code, I just have the one program that does everything and I just have to feed it the right data, is that the fusion that fuses the Harvard architecture and the von Neumann architecture? And so if I were retired, that sounds like a cool project, which I would have to do using GPUs and mobile devices, which were my first two things, which is why I started there. And what would I do with that? Well, if I weren't retired, I would try to figure out how to monetize it. But I am retired, so I don't have to figure out how to monetize it. So I'm just doing it for the art. Thank you so much for your attention, and I'll be hanging around to discuss further.
Can I have my laptop on? I have a joke. So I was emailing Rommel to find out what today's talk would be about, and while you had no idea what was going on. Everybody, please thank Rommel.
Thank you.